start. First thing I want is to make a correction from last time, like official. We discussed it in the beginning of seminar, but the definition of the push forward of a section was not correct. So push forward of vector field. It's push forward of vector fields. Correction. Okay, so what's the setup? Let's recall it real quick. So we have a smooth map, and so we want the map F over star, which goes from vector fields on M to the vector fields on N. So one thing to the new thing that I didn't spell out is that in order to construct push forward, I need F to be diffeomorphism. So F diffeomorphism. And this is why. So what was the definition? So I thought about vector fields as derivations, and then okay, so the definition that was given is like that. So I take derivation, and corresponding derivation here should eat something from C infinity of n, right? And we need to understand what this should be. So this what I put on the board was this d of h of f, which is actually so what I should get is a function on m, right? So function on n, right? So I take f star d, apply it to function on n, I get a function on n. But let's see what's happening. So h composed with f is a function on m. Then I apply d, which makes a function on m, right? So something is wrong here. So actually, now I think, well, I need to take this as a function, right? And now push this forward. So I use the same notation, but now I'm applying this not to vector fields, but to a function. But applying this to a function, so okay, this is the same as, you know, like this is a particular case of push forwarding, actually, differential forms, but okay, we didn't discuss it. So in this case, what I need to, so f star, how do I define it from C infinity of m to C infinity of n? Well, I just need to precompose with f inverse. So I take something from here, say g, right? And then I take g and map it to g composed with f inverse. Right? So if I do this, so this should eat a point on n, right? So it goes from, so I have point on n, by f inverse it gives me point on m, and then I apply g. And then when I apply G, I go to scalars, to R. So yes, so it works like that. Okay, so this is some correction, since I said something which made no sense. Now let's go back to pullback of K-forms. Well, we discussed only pullbacks of one form. So now pullbacks of differential form. Right. So again, the setup is the same, except now we don't need to require F to be diffew. So this is smooth map. Okay. So right. Well, first of all, I need to discuss what does it mean. So if I have, so first is kind of natural construction. So if I have two differential forms, one from well, of degree k, say on M, and another one, eta, it's of degree L, some other degree. On, well, yes, maybe I'm jumping a little bit forward. So okay, so anyways, let me postpone this, because okay, so I need to think about forms, well, as some maps from the base to upstairs. Okay, we discussed that for one form, so okay, let me spell this out for K forms, right? So anyways, we so if I have little detour, so let U phi be a smooth chart on well, let's talk about this manifold M, right? And let x1 blah 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 x, I don't know, M be corresponding coordinates. So, and let me fix some indexes I1, Ik, so they are so these are from the set 1 blah 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 M, and let me think that they're distinct and they actually are ordered. So I have I1, I2, and so on, Ik. Okay, and then I consider the following map, which I denote dx1, dxi1, which dxi2, and so on, dxik. So this is a map from where to where? From U to disjoint union over all points in U of I need to take well, dual to TP U, And moreover, I have to take it. So interesting. Can I move? I don't think so. Okay. So I make this a little bit further. So I take kth antisymmetric exterior power of T_P star U. Okay, so well, the map is clear because we know what are these dxi's. So it just takes a point and gives me an element dxi1 p. Its value at p, right? So this is a map from U to TP star of U, right? So I just consider the wedge. And the wedge, like in vector spaces, because I fixed the point, dxi2, and so on, and dxik. Okay. Then I just say that similarly to one forms, I should say that K forms are can be identified are so let me just write are can be identified with maps. Well, omega from so K forms on M, right? And so this is from M to the disjoint union of over P from M, and then lambda K T star P M, right? Such that well, omega restricted to any Q, so this is coordinate neighborhood of some so this I have coordinates on U. It's just given, so it just can be expanded as a linear combination over C infinity of M of these things. So this will be F, well, okay, so I should write it like this. Sums over I1, I2, Ik, F I1, Ik, dx I1, dx Ik. And this guy, well, it's, so let me just say that this belongs to C infinity of U. Okay. So now, once you can think of forms as certain, well, I can think of what is a value of a form at a point. It's here. So now I can just, well, and again, well, omega of, so omega p, right? So this will be, so it's notation for value of omega at p. Okay, and then now what I need out of all this is that if I have now omega, which is k form on M, and eta, which is L form on M, well, now I can understand what is omega wedge eta. Right. So, well, I can understand that point twice. It's just, well, it's just at point P. So it's just definition. Omega P wedge eta P. Okay. So now, when this is being said, so now I know what is a wedge. I can now define. So define pullback as unique R-linear map. Well, we'll write it with upper star, and this is from where to where? From omega, well, from the sum over all omega k's. It's better for me to write it like that. So sum over all k, omega k. Well, it's pullback, so it's the arrow should go backwards from n to m. So like that, omega k of m. Satisfying the following three things. First, well, I define it on zero forms. So zero forms by definition. So these are just smooth functions. Okay, and then so for zero forms, I just define f star of h is just I just compose it with f. So for any h from omega 0 of well, in this case should be n, right? And second, I need to well, conventional behavior with respect to wedge, taking wedge. So f star of omega wedge eta is f star omega wedge f star eta. So this is for any omega and eta. So these are forms on yeah. So when I don't write indexes, it's just sum over OK. Okay. And third, so this we just need to use that we already defined it for one forms. Okay. And so for one forms, definition is as before. So we need to check that it really exists and unique, right? Well, existence you just can define it in a very natural way locally, right? Coordinate-wise, right? So just let me try to. So existence So you just define f star omega. Well, so if you have if you can write omega on some u as follows: sum over f I1 blah 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 ik, right, dx I1 which dx ik, right? Then I just defined f star omega. Well, I defined just on u. Well, as follows. Well, it's defined for 0 and 1 forms, right? So I take, this f is not very good, so maybe I need to take some other coefficients here because my map is also f. Yes, so I have, well, f star is good, so I have f star of h of I1 over ik, right? And then I apply f star dx I1, which f star dx I2, and so on. And okay, it's clear.
What are
Yes.
the indices that you're using for each sub-indices?
Sorry, it's ice. It's hard to. Yes, so let me make it more clear. So I1, IK. Yes, and actually I have to be, I guess, more accurate, right? So I have to, specialize to u. So this will give me a smooth function from u to n, and then I actually can, apply this. So I know everything is defined on 1 forms. This defines it on 0 form. So okay, it's defined locally. Now I need to check that on intersection it's defined. Well, it's well defined. Okay, I will not do this. And then what about uniqueness? So then it's plus check. Well defined. Well define this on intersections of charts. I don't know if well-definedness is a word, but no. Anyways, uniqueness. And uniqueness just follows from the following lemma. From lemma. I want this. That suppose I have a form eta. Well, it's a form. We'll say on n is such that it is actually is not supported on some open interval. So it restricted to u is 0 for some u in m. Then f star eta restricted to u is also 0. Okay, you might think that this is obvious, but this is not actually, well, it's easier as one line proof, but still needs need to be accurately said, because what I said here is it's R linear, but not C infinity over M linear, right? And this makes a difference. So if it's C infinity over M, of course, just then 0 goes to 0, just you know, linear map for one vector space to another should do. But here, well, something should be checked. That's okay. The computation is the following. So if I have wow. So if I have some point P, well, in U.
За нас после быстрочки, в общем, там у нас pullback от сужения.
Да. Нет, это pullback.
И это сужение pullback, это относится к
и
сужению
потом
pullback, то сейчас уже у нас это на M, а нам...
Если pullback сужение, тогда точно 0.
Ну да, это.
Вот.
Сейчас.
Тут
Там,
нет.
просто и там сужение на U, но где-то же сейчас.
То есть я беру это на всем, применяю F.
Не, я имею в виду, что, наверное, где-то должно быть F на ту или, ну, в смысле, что-то, или F минус первое ту сейчас, ну, уже оно под множество чего? M получается, а у нас где-то, наверное, будет N.
Ну, да, я должен, okay, yes, this is fair enough. So I need to take restricted to V, okay, for any V open in F. Right?
То есть у нас отображение из M в M.
Сейчас. Okay. Let's think. So I have F, which is from. Окей, давайте аккуратно. Значит, чтобы действительно я тут, возможно, запутался. Давайте. У нас F is M в N. So we have F from M to N. Then, right, so this should be in N. So this should be in N, right? Because pullback goes back, right? Okay, so let me.
So это originally from omega of F, right?
Yes. Okay. So I need to follow my notes because everything is written okay there. So I need to change this. Sorry. To N. Is such that eta restricted to U is 0 for some U in N. Right? Then F star eta restricted to V equals to 0 for any V
And just write fin
such that F of V.
inverse.
Yes, so let me. Well, F inverse,
But
yes,
just
or I can
definition of,
write it like
fin
this.
inverse.
So, open or not open is just phi.
Can we not even use V notation and just strictly write phi minus phi inverse of U?
Yeah. Well, yeah, you can put the inverse of U here, and this will be even easier, right? Anyways, so for any V such that this happens. Okay, well, this makes more sense. Now, okay, quick proof is that, well, okay, I take P from P from where? So I need to take from V any, so any point. Right, then f of P is inside U. Right, and then I would like to take psi, which is well, it is from C infinity of n well, such that support of psi is inside U, and psi is equals to 1 in some neighborhood of f of p. So so psi restricted to U tilde is 1 for some U tilde containing f of p. Well, it's the fact that I can find such thing is okay. It's some technical maneuver that is rather related to multidimensional calculus, right? But there is some, you construct such thing with the help, if I remember well, of a function e to the 1 over x, something. It's like standard procedure. So it's a code bump function. So it looks like that. So if you have one open subset of R and a little bit smaller, you have smooth function such that it is 0 here, then something in here, and then 1 in here. So this is my psi. So this is U in this case, and this is U tilde. All right, and so then I just do what? I just take psi eta. What is it? Yes, it is right. So this is actually 0, identically, right? Because eta is 0 on the support of psi, right? And then I take f star of it. Well, anyways, this is 0 at my point P. Right, because this guy is just identically 0. On the other hand, I just use my rules. Basically, I just need the second one from there, this one, where this is 0 form, right? And then it just reads like that. It's f star psi at P, f star eta at P. And then this is, so this guy is 1, right? So f star eta at P, so okay, times 1. So it's just 0. So for every P, so this is for every P from V, we can do this. And so that's the proof. Okay, is this clear how from this lemma the uniqueness follows? For everybody.
Just taking the difference.
Yes. So basically, so by these rules, uniquely pullback is uniquely defined for anything that is a wedge, like linear combination of a C infinity of M of 1 forms. right? Because, well, I just, do it by deduction because on one form I know and on zero form I know, right? And, but not every, so the only technical thing here is to understand that not all K forms are wedges of linear combinations of wedges of one forms. Because this happens only locally. So globally you don't know how they look together. Okay. And then right. And so you have so you just take well you just take some okay well you again use bump function, right? This one. Or maybe I can write it here. Right? So you have omega, right? And locally you know that it is wedge, linear combination of wedge of one forms. So you know it for some, you know that a pullback is uniquely defined for such thing, where psi is some function like that, such that it restricts it to coordinate neighborhood, right? But then, indeed, you just apply this lemma to this guy, right? And then pullback of this, which is uniquely defined, is just equal to the pullback of this. Well, on the restriction to this guy.
If you look at this one more time,
Mhm.
imply the pullback of the union is equal to 1.
Pullback of the this one, because it's just constant function. So if you compose anything with constant function, it just is also constant. So what is a pullback of function? You just compose it with this file, right? So composition of the constant function is constant function. Okay, so apply. So okay, let me just summarize it like that. Apply lemma to this. Then uniqueness follows. If you need more details, let me know. We discuss it. Okay, so now let me continue. The next thing that I need to introduce is exterior derivative. So for any k from 0, so this is from 0 to m minus 1. So m here is dimension of a manifold m. Define the exterior derivative as d as the unique well again R linear map.
Should we use the index key somewhere in
We might, but we will abuse notation as usual. In co-chain complex, your
sorry, I got it.
co-derivative is usually this a bunch of different maps, but the index you can drop the index. Okay. But you're right. Like if you want to be pedantic enough, you should write k here.
No, I just mistook for another derivative.
Yeah. So unique R linear map. Well, so this is d from omega k of m to omega k plus 1 of m. I'm sorry, I messed up this index. K plus 1 m. Satisfying the following things. So first, again, if I have f which is 0 form, which is just smooth map, then df, well, we just define it like that. So at the point P, it eats a vector V. This is vector from the tangent space at the point P to M. So this is just V applied to F. Well, at point P. Second is if I have omega is K form and eta is L form, then I just define d omega wedge eta as d omega wedge eta. So we just use some kind of Leibniz rule, but with a sign. So plus negative 1 and here to the power k, where k is this one, omega wedge d eta. And number 3, d squared is 0. Yeah, and that's it. So these 3 things. And again, you need to, the idea is the same. You need to check existence and uniqueness. Again, you just define it locally, check on intersection, and uniqueness, you need the same kind of lemma that we proved here. Right, well, it's I guess, useful to define it, to look how it should be locally, right? So existence so if I have omega, well, suppose I write it locally, so it's sum with some coefficients, and then I have dxi1, dxik. Well, maybe I don't even want this sum, right? So since it's R linear, I can just right. So let me just get rid of unnecessary stuff. So suppose that omega is like that. Because it's R linear, well, it extends linearly to sums. Then d omega is just what? It's a sum over I from 1 to m dh over dxi wedge this whole thing. So that's how you compute it locally. And then, again, we check that the intersections, everything is fine. And the uniqueness is again by lemma, well, of the same kind. So if you have eta such that, well, it's from omega n, right, such that its restriction to some u is 0, and then d omega, well, I don't know why so there's only one manifold now, M. So it is from M. So d eta restricted to u is 0. Right, and the proof is just this of the same kind. Computation is a little bit more fun because now we use Leibniz rule, and there we don't even use that psi is constant, really. But here, this term will be gone because psi is constant. So you just apply d to psi eta, right? You have d psi, which will be gone, and then this will be 1, and this will go to 0. So this is the same computation, but you need to use Leibniz rule. So proof similar to previous lemma. Just use Leibniz rule. Use Leibniz.
That must be, I think, F inverse of U, the restriction of the
No F. It's easier now. We don't have to think about where we leave M or N. Everything is just one M. Right. Next thing that we want is this proposition. Which says that for any f from M to N, we have, so full x commute with D. That's it. F star D is df star. Okay, so let's exercise. We just need to exercise in applying these rules for F star visible, right? So let's prove so we need to prove what that F star D I don't know some sigma is D F star sigma for sigma supported on a smooth chart. And let's prove it by induction on the degree of sigma.
This sigma plays the same role as C before.
No, S is just some. So sigma should be a form in N. So sigma is from omega N.
It does not have.
It's not psi was function before. Psi was 0 form, but this is just some form. Well, so what does that mean? So these are two linear. These are composition of two linear functions. So we need to apply it to something. We need to apply it to a form. Well, we just need to see. So since we're applying pullback here and here at some point, the form should sit in M.
I mean, support means that anywhere except for this chart, it is equal to 0.
Yes.
Uh-huh.
Well, anyways, I can write it as a linear combination of wedge of one forms. That's the only thing that I need. Right. Because I use induction, so induction, I use Leibniz rule for induction. So anyways, base of induction, so I need to check that, so I need to take sigma to be just G dx. Well, for some coordinate x, right, where it's support, right? Then, so we just apply and check.
Shouldn't we start with just a function?
Was it?
You took one form.
Yes.
Shouldn't we start with 0 form?
Zero form will not give induction, because anything plus 0 is this anything. So we want induction, right? You need to wedge with one form to increase degree. Wedging with 0 form will not get you anywhere. Well, you can start with 0 form, but it will not give you induction. Anyways, so let us. So first let us see df star g dx. This is d f star g, and then f star dx, right? Right. So this guy. So okay, let me just write it down. So I just want to maybe write it like that. So if I have right. So it is. So what is f star of g? So it's just d. So okay, like that. D, and then I need to compose g with f. That's it. So this guy, with this f star of dx, well, I claim that this is just x composed with f. Right, x is a coordinate, so I can think of it as a function, right? So it's like that. Well, it's we need to check that, I guess, right? So. Right, so from here, so that this guy equals to this guy is clear, right? So we have some definition how f star acts on one forms, so I guess we need to check that this equals to this, right? Okay, let's do this. What should I do? Yes. So I will be more, I guess, general and see what is f star dg at the point P. So I need to apply it to some vector v. So I need to recall my definition on one forms, right? So it will be dg, and then f at the point f of p, and then apply it to df of e. So this was our definition on one forms, right? Okay, then I need to recall what is so dpf here, right? So this is okay. So now I need to expand the definition of a differential function, right? So this will give me dpf of v, so this is some vector, right? I need to apply this guy to G at the point f and take its value at the point f of p, right? So this is just a definition how differential of a function works, right? So I just take this vector, apply it to this function, and take at the point f of t, right? Okay. And then, but then this is just right. So this is now I need to expand this, right? So I have this is f yes. Well, it is already the point f of p, so therefore this I can actually even erase. Right? So this is already a vector applied to G, and this is already tangent vector to point f of p. So it's a derivation and point f of p. All right, but then this is I need to expand this. So this is by definition again of df. It's just v, right? And then I need to apply to f composed with g, actually. Sorry, the other way around. G composed with f. Not here. So this is v of G composed with f. Okay, so what I'm proving is that actually I can replace this with this one, but G is my x in here. Okay, so and then, well, I'm just using my definition of differential of function 2 times, and also definition of back of 1 form. Okay, so anyways, this is one side. What about the other side? So I need to take f star of d and then g dx, right? Well, it's like that. So it will be f star of dg wedge dx, because and then d squared is 0, so therefore this is only that. Okay, so then by definition it's just f star dg wedge f star dx, right? Dg here, and then this is just again by our computation here, right? I need to write it as d of g composed with f wedge d x composed with f. And okay, I compare, and so therefore this guy equals to this guy. Right? Okay, so this is some exercise. Yes, I just need to use my defining relations to see that everything works. So I'm trying honestly to do that. Okay, so let's prove the step of induction. For the step of induction, I need, again, I need to use Leibniz rule, right? So we can assume that sigma is actually omega wedge eta, right? Where, well, both omega and eta have positive degree, right? And then, well, then I just, check that D, I don't know, maybe this one I will skip. So this one is really, really clear. So then I just check that df star omega eta. Well, I just need to, to maybe just to begin the computation, f star eta wedge f star omega f star eta, and then I use the Leibniz rule, right? So it's df star eta wedge f star omega plus minus 1 minus 1 to the degree of omega here. Now pull back respects the degree, so this really will be degree of omega, d f star of omega, of eta. And then by induction I can pull these f stars, and then by Leibniz rule, get it all together and can complete the proof. So, okay, let me not go further. All right. So this is for sigma supported on a smooth chart. What should we do for any sigma? Это слишком круто. Две единицы хорошо, да, но нам даже этого не нужно. Нам нужно просто, okay, for uniqueness we just need to combine these two lemmas that we proved before, right? So we have this lemma that actually if something is supported on a neighborhood is 0, then d is of that on this neighborhood is 0, and f star on that. So we need to apply this to lemmas twice, and this will give us the proof. So proof for any sigma falls from two previous lemmas. Okay, do you want me to give you more detail?
I have a question.
Okay.
About why can't we start with zero forms? This is because one forms are not all one forms are differentials of zero forms. Because of this?
No, not because of it. Because we want to use an induction. So how do you use induction if you don't prove it for one forms? So your second step of induction. First step of induction is zero forms. So how do you prove it for one forms if you prove it for zero forms? You want to use a wedge, right? Okay, you
yes.
say, okay, my one form is a wedge of one form with zero form, but again,
right.
you don't move anywhere, you don't move one step back.
Thank you.
All right. So, again, do people want me to give more detail or just, okay, Seems like everybody is bored to death, and so we can work in that new definition. Anyways, so let's move on. So next thing that I want to talk about is the RAM homology. So we finish at 11:30. So we have cochain complex. Like that. So 0, omega 0 of n, omega 1 of m, and so on. The last one is omega m, right? M is dimension of m, and then to 0. So what are these maps? These are our exterior derivatives, and actually here as well, right? Well, when I say that it is a conchain complex, so what does it mean? D square is 0, yes. So yeah, I'm using this one of defining properties. Yes, and so then we define the RAM homology as homology of this complex. So we define homology. So HK of M, well, it's cohomology, so I should write this here. So this is just, well, as usual, image of D. Well, here indices would be handy, of course. So maybe, but let me just denote like this. So D, which maps from omega K. So image should be in, so this image should be in K, so from K minus 1 to omega K, quotient by the kernel of what? Of D, which is from omega K to omega K plus 1. Okay, and then what we proved in the previous proposition is that if I have a linear map from n to n, such linear map induces homomorph. Well, so this is what as an object. So these are all real linear vector spaces. So this is also a real linear vector space. And F induces a linear map. F, well, we denote it as well. F without a star.
I'm sorry. Ну, наверное, мы хотим, чтобы хотя бы, ну, обычно, когда так пишут, имеется в виду, что начало, по крайней мере, слева точное, но у нас функции не вкладываются в форму, и, наверное, может быть, слева вместо нуля стоит писать скаляры.
Да, это правда. Сейчас. Нет, а что значит не вкладывать? Но мы же не вкладываем.
Ну, я имею в виду, это не вложение там, вот, собственно, дифференциал от константных функций.
Нет, я хочу, чтобы если я дифференцирую, если я дифференцирую функции, я хочу, чтобы все было ядром.
Ну, то есть все скаляры, собственно, да, в ноль отправляются. Ну,
Ой, нет, я хочу, чтобы ядро было нулевое, да? Если я так пишу, чтобы у меня
ну,
точно
да, вот
последовательно
обычно,
было.
да, ну,
Да. Значит, я должен тогда что поправить?
ну, видимо, вместо нуля R написать и 0 перед R. Ну, и это действительно же так, как сказать. Ну, если вообще пучки рассматривать, там действительно первое...
Ну, вот так, да?
Там первый пучок будет не омега 0, а R, да.
Да. Так, и тогда как вот это...
Ну, и тут, наверное, можно...
Нет.
А, как назвать это? Упражнение.
Нет, что это за отображение?
Ну, число отправляется в постоянную функцию.
Нет, нам как бы... нет, вопрос, что такое H0 тогда, да?
А, H0, ну.
Ну, H0...
В чем проблема?
Нет, проблема в том, что если я напишу 0, то это не будет... Сейчас, ну, мне не нужно точно последовательно.
Ну, да, ну, обычно говоря, пишут на, ну, точно слева. Ну,
нет, проблема в том, что я хочу назвать H0, правильно?
Ну, да.
Просто минус
Вот.
первый член выходит.
Да, но вот мы хотим, ну, H0 это все такие функции, которые, значит, при D обращаются в 0. Ну, вроде это нормально.
Мне кажется, вы там ядро создали
Где? А, здесь? Сейчас, давайте проверим. Значит, у меня, действительно, у меня образ в ядре, да. Да, так что здесь, вот, во-первых, ядро с образом. Это более очевидная поправка должна быть. Так, теперь вот это. Ну, значит,
Ну, а у H0 ядро, ну, то есть тут числитель просто нулевой, что было до поправки, что после поправки остался.
ну да.
Ядро там.
Ну да. Ну то есть, как бы, в принципе, мне даже это не нужно было просто.
Ну, в принципе, да, но там, если вы такую позовете для пучков, то, ну, она действительно же с R начинается. Ну, для пучков там будет локальный постоянный.
Ну, мне важно действительно, что какой, значит, образ здесь. Вот. Ну, и образ, как бы, но мне надо как-то это написать. Что не напиши, я хочу, чтобы вот это отображение было нулевым.
Сейчас, наверное, если мы ошибку посмотрим, то это будет. Это будет не то.
Вот. Ну, что я здесь напишу? Ну, я могу 0 написать, в принципе.
Ну,
Как что-то больше нуля писать, я не вижу смысла. Окей. Ну,
ну, то есть это сейчас означает, что эта последовательность никогда не будет точна. А обычно там утверждение в таком виде, что для, ну там, я забыл, как называется, не полкера, наверное, что для Rn эта последовательность точна, но в таком виде она не точна никогда. Вот из-за этой левой части. Потому что у нас омега-0 и омега-1 не вкладываются по действию омега.
ну, надо константы.
Ну, это, конечно, как...
Ну, надо как бы константы вложить, да.
Софистика, что мы просто в этом месте напишем, просто, ну, и хочется сказать, что вот в случае Rn это всегда точна, но для этого нужно все-таки, да, положить туда константные функции. Ну, вот, как бы,
Да, я думаю, что да, наверное, да, я думаю, что вы правы. Но единственное, что значит, что значит, что у нас константы, конечно, ну просто вложение констант, да, правильно?
ну, да.
И, в принципе, нам это ничего не портит. Да, хорошо. Тогда давайте вот так сделаем. Okay. Значит, okay, okay, discussion was in Russian, but it's clear what happened. Informal. the result. But okay, let me think about that more. What I want from it, and maybe correct it next time. But okay, so far let us take this, because indeed lemon Poincaré I wanted to work for in degree 0 as well. So then I need to take it like that, right? So what I have is that I have a map F. If I have a smooth map F from M to N, then it induces linear map from the homologies of N to the homologies of N. Right? So, well, I just take a pullback of forms, and since it just kernels and images of D, the invariant subspaces of pullbacks. Maybe let me say it more clearly. Is that, or I guess it's clear. So I guess, so if I have image, so I have F star D equals D F star. And so what I said is that F star of the image of D is inside the image of D. And F star of the kernel of D is inside the kernel of D. And so therefore, I can take a pullback and canonically introduce the linear map on homologies, right? And well, okay, usually denoted by the same letter, F upper star.
Сейчас тут, еще чисто, что поменяли, собственно, не должны были поменять видос образом, но у нас теперь еще синтаксисная проблема, да.
Да, теперь синтаксисная. Ну давайте К с К у нас. Ну нужно как бы не только вот это поменять, а вообще все. Значит,
нужно...
давайте. Значит, К плюс 1 здесь. А здесь К минус 1, здесь К. Так. Okay. Right. So 5 minutes left. But here is the theorem that I don't know. Maybe I'll prove next time, maybe not. I'll think if it's reasonable. But the proof is not so hard. So suppose that I have two homotopy. So homotopy between two maps from M to M. So I have F from M to N, and G from M to N. Okay, and so they are smooth and homotopy equivalent. Which means what? It means that there exists a smooth map H. It is map from interval I. Well, interval or R, I don't know. so maybe m times interval to n. So it's smooth map such that h of p0 is f of p, and h of p1 is g of p. So I here is just an interval from 0 to closed interval. And so this is what it means that f and g are homotypic equivalent. Then reduced maps on homology are just equal. So then f star equals to g star. So these are induced maps on homologies. Right. Well, this is Poincare lemma, right? Because well, for what you said for R, you need to homotopy to a point, right? Okay. Well, let us stop the lecture here. Okay, let's have a break. We don't have time. Let's do prove it right now. So maybe next time.
Ладно, может быть, все-таки с нуля нет, потому что кажется, что H0 должно быть количеством координат связности. Ну и тогда, если у нас многообразие связано, то должно получиться красивый координат связности, то должно получиться просто R.
Ну, обычно так, да.
Ну ладно, да.
Ну,
Просто меня смутило, что, ну, если мы хотим точно связь пучков, там все-таки будет как раз вот этот R, локально постоянный. Ну, а потом уже будет омега 0, омега 1 и так далее.